Wherever you go, there are things in nature that you can see, or things that you hear. Things that sort of grab you and put some question in your mind. For example, you see a rainbow. I mean, they're this wonderful, mysterious thing. But why? Why does this happen? And you find out it's because of the way the different colors get separated inside of a water drop. Understanding what's going on in nature, that makes you more at unity with what is around you. That's what science is about. And sometimes, when you look at the world, you're going to learn something brand new, something nobody has ever seen before. And that's what this whole story is about. So, when I was a kid, I was sort of a lousy student. School was quite rigid, and grades were a thing that some people made a big fuss over. I just couldn't see it. But I got mixed up with electronics real early in my life. There was a section of New York City which, for nickels and dimes, I could buy all sorts of wonderful electronic junk. You could make almost anything you wanted. And so I learned most of the things that I learned in my life by building something and then trying to make it work. So I came to MIT, and they took me, which is sort of miraculous. I don't know why, but they took me. And I became a physicist by default, because it looked to me like physics was a place where you had a little more freedom. And that's where suddenly I got my education into what became permanently part of my life. And it was the Einstein theory of general relativity. Now, general relativity is tricky, but the way I can best explain it to you is that it was a completely different conceptualization of how gravity operates. So, for Einstein, the way he thought about gravity was it actually distorted space and time. Took straight lines in space and made them curved lines. It's a thing that actually changes the realm of nature. At the time, it was just unbelievable, shock-worthy stuff. But it turns out he was absolutely right. I mean, you have to understand, Einstein had an intuition that was remarkable. He understood nature in a visceral way, almost like he had a direct pipeline to God, if you want to call it that. Then, in 1916, he writes about something called gravitational waves. He recognizes that matter makes waves when it gets accelerated. And it travels at the velocity of light and stretches space in this dimension and compresses space in that dimension. And it goes through everything. Nothing stops the gravitational waves. But then he comes to the conclusion right at the end of that paper, he says, look, this new thing I just invented, this is never going to amount to anything you can measure. It's just too tiny. It's hopeless. But the fact is that, in this case, Einstein was completely wrong. And that is really the whole story of LIGO. Anyway, so let's get back to MIT. Eventually, I became a faculty member. And I was asked to teach a general relativity course to graduate students. And as the course wore on, the students asked me how you would make a device that can measure gravitational waves. So I remember on Sunday night, and the lecture was on Tuesday, it suddenly dawned on me, maybe the right way to explain this is really simple. You put a mass over here, and you put another mass over there, put a mirror on this, and then you take a light source and measure the time it takes the light to go from here to there and back again. And now what happens is let a gravitational wave come down on this thing and change the spacing between those two masses. And that would change the time it took the light to go back and forth. Very simple calculation. I said, that's the way to do a gravitational wave detector. Now you understand. So I said, okay, I'd like to build a prototype.
So one of us has to stand on the table, huh?
And it eventually came clear to me I had to have 3 masses, so you could measure both the stretching of space as well as the shrinking of space, and then you could compare those two. I clearly had to use lasers, And then we had to measure the tiny little motions that are associated with the gravitational wave. It's about 1,000th the size of a nucleus of an atom. Such a small fraction that nobody can conceive of something so small. And measure it, that's crazy. But anyway, we built a prototype and we started operating it.
So the laser is here, and the light comes out and it goes screaming through a whole bunch of stuff. And the first thing is rays, phase-modulating crystals.
But at the same time, there was no support for this crazy research because I wasn't saying we're going to see gravitational waves with it. I couldn't. I would have lied if I said we have the technology now. We had another factor of 1 million to go. People threw us out the door when we told them that. But the National Science Foundation started funding me at a reasonable level so I could start building bigger detectors and a bigger team.
I first met Ray Weiss as a first-year graduate student at MIT. And when I talked to him about gravitational waves, I actually thought he was really just crazy because it was such an impossible measurement to make. But if it worked, it was really going to open up a completely new window into the universe. So, I mean, who can resist that? So when I joined, I was part of the team that built the LIGO Gravitational Wave Observatory that was proposed by Ray Weiss in the early 1970s. He proposed that you had to use very long detectors. So we built these 4-kilometer-long facilities in Washington and Louisiana that were large enough that it became kind of possible to think about detecting gravitational waves from them. But at the same time, there were no guarantees that we'd see anything. We knew we were charting unknown territory. So LIGO is a gravitational wave telescope. And because of Einstein's theory, we knew that out in the universe we have black holes. And black holes, in some sense, are the most gravitational object you could imagine. They have so much mass in a small volume that even light can't escape their gravitational pull. But by the 70s and 80s, we had the theory that black holes can exist in pairs, orbiting each other. And they get closer and closer, and they orbit faster and faster until eventually they collide. And in that process, they radiate these ripples of space-time that travel to us, and we here on the Earth get rocked ever so slightly by the passing gravitational wave. And then in the detector, those mirrors will move closer together or farther apart. And so our computer would see the signal, which is just a series of peaks and troughs that were growing in size and getting closer in time. So that's what we were trying to see. But let me just tell you, no one had ever seen two black holes collide, and it was seen as something that was a pretty long shot. So yeah, I had moments where I would really question, will we see these gravitational waves in my lifetime? Because even if it occurs in nature, we weren't sure if the instrument would be sensitive enough. But here we were in September 2015, construction was coming close to completion, and we had to at some point say, okay, the improvements are going to wait, we're going to turn on the instrument. And then overnight, the instrument registered something interesting.
Whoa, what's that? What's happened? I go to the computer and I look at the screen, and lo and behold, there is this incredible picture of the waveform, and it looked like exactly the thing that had been imagined by Einstein. Now, I have to admit to you that I was still skeptical for a long, long time, because especially with so many reputations and all the beautiful work that had now gone into this thing, we did not want to come and make a false detection. But eventually it came down to the point where we began to believe it.
Ladies and gentlemen, we have detected gravitational waves. We did it. scientists have announced what may be among the greatest discoveries in the history of physics. Gravity waves, predicted by Einstein but never observed.
My first thought was, too bad Einstein isn't alive anymore. I'd love to tell him about it. And what would he have said? My guess is that Einstein would have been tickled pink, but also very skeptical and want to know exactly how the technology worked. That's my guess. And then it only slowly dawned on us that we had made new science. Science which is really at the basic core of the fundamentals of what makes nature operate.
The Royal Swedish Academy of Sciences has decided to award the 2017 Nobel Prize in Physics to Rainer Weiss for the observation of gravitational waves.
You know, Ray Weiss knew how to measure gravitational waves in 1972, and he's been going at it ever since. And so, thanks to this work, suddenly we have developed an entirely new sense for observing the universe. We are hearing gravity for the first time. And in some sense, we may be able to sort of hear the assembly of the first galaxies to try to understand how our universe came to be and was assembled. It's pretty amazing.
I think the science of physics, the natural philosophy of the universe belongs to everybody. Belongs to you, belongs to me, belongs to everybody. But I mean, I am 87. And so this new science is something which is a challenge to the young people. That's the future. So, now let me ask you a question. With gravitational waves, you have a new way to look at the universe. You can see all of what nature has in store. So now comes the question, what do you want to find out? It's going to be spectacular, I think.